For those of you who were not here yesterday, my name is Theophilos Maritaras, and I'm a computational scientist at CSCS. So today we're going to see together how we can use Numba to accelerate our Python code. First, the CPU-only version, and then we're going to look at GPUs. At first, we are going to say some general stuff about GPUs so that all of you who are not familiar with GPUs can be familiar quickly. And we will start with accelerating our code using GPUs with Numba. And then in the afternoon, we are going to show another library, which is called CuPy, which is a drop-in replacement for NumPy, but for use with GPUs. So let's start by first updating our Git repository. So I just go here to my repo, and I will make sure that my repository is up to date. So make sure that you have the latest changes that I have made yesterday. And in case you have questions, please ask at the question and answer channel, the Q&A channel, and I will answer. Raphael can answer if it's something specific, or it's something more general. I can stop the lecture and answer for all of you. So please make sure that you go to Numba from the Python HPC repository and go to Numba CPU. And we are going to start with the first lecture, which is Numba CPU. So you can see it here. And just make sure that you're using the correct kernel. This is the kernel that we have created for you. If you have not already created, there is the information on the general channel on how to do so. And so is everyone ready? For those of you who are not ready, please say so at the question and answer channel. Okay, I don't see anyone commenting. So I guess we are ready to go. Okay, so as I said, today we are going to start with Numba, and as it's written here, just-in-time compilation with Numba. So what is Numba? Numba is JIT, short for just-in-time compiler, which translates Python code in native machine language. So we are going to see how we are going to use special Numba decorators, which are provided by the library to accelerate our code by compiling it natively to machine code. Numba is compatible with NumPy arrays, as we are going to see, which are the basis of most of the scientific packages in Python. And it enables parallelization of machine code so that all the CPU cores can be used, so that we get the most out of our computer. So is the size okay? I believe that the size is okay. So here I make some boilerplate imports, and I just import number. So let's do it. And here I will create a new random generator, which I'm going to use throughout the notebook. And this is the way to create an object which will give us the randomness that we want. And we can use it to generate random numbers from the distributions that we want. So we saw yesterday at the Python course that when I showed you how to compile Python code outside of the Jupyter notebook, we had a function which calculates whether a number is prime or not. So I have the same function here. This is pure Python. I run this so that my function is ready. And now I create a random integer between 2 and 10 million, and I check whether this number is prime. So I check, and this number is not prime. And just to make sure that I try to run this here, it does not like this thing here. So we're going to change it, but I wanted to show you how we will start transforming this Python code to number. So let me convert this to an F string, and this should be fine now. It's prime. So you see it gets an arithmetic error exception because, of course, we cannot test if one is prime and is prime. Then it will tell us false. I just replaced the string here so that it's clear. Okay. So now I'm going to use the same function, but I'm going to decorate it with number JIT. So this is the only thing that is needed to just in time compile our number generated function. So you see here, I just added the number JIT. The function is more or less a copy of the original one. And now I'm going to time these two functions. So it throws some number deprecation warnings, but don't worry. So let me rerun here. So you see that the first is prime. The time to check for 10,000 random numbers whether they are prime or not. The original Python version, it took 82.2 milliseconds, and the JITed one, just by adding number JIT here, took 82.2. So just by adding this number JIT, we got about 5 times speed up. So as everything is fine to now, everything can run this. Everyone can run this. Okay. So let me rerun. And again, we get the same results. But here you see that when I went and compiled first, defined first the function and then run, you see that the first, don't care about the warning for the moment. The first run, which is the pure Python one, took 85.2 milliseconds, while the number one took 475. So now it's much slower. So let's run once more. Now it's much faster. So this is where the JIT meaning comes in. So JIT is just-in-time compilation. Just-in-time means that whenever the compilation is not happening when I define the function here, but it's happening the first time that the function is used. So you see that when I define and run for the first time, the time it takes is much larger because this time includes the compilation time. So from the second time and on, you will see that I get the good performance that I'm expecting. So Numba JIT has two modes. The one is the Python mode, the object mode, where more or less all of your Python code, most of your Python code is valid Numba code, but we want to get even more performance out of Numba. So JIT has an option that no Python equals true, where I tell Numba that I want to go out of the object mode and compile as much as I can to the machine level. So let me define this. Here I call it njitted, and let me run. But now tells me that it failed in no Python mode. The reason for that is that we cannot use Python objects in no Python mode. So this thing here, it's not possible to do in no Python mode. So I converted this to a normal string without doing the Python formatting here. And I will recompile. Here you see I use njit. So this is equivalent to using Numba JIT with no Python equals true. And this is just an abbreviation because the developers of Numba know that we want to accelerate the code as much as possible. So we have this njit directly without having to provide the no Python equals true. So let me compile this now and run. I run. So the first time you see 97.8 milliseconds. It's even slower than the first JITted version. And let me run again. And now I have the JITted version and I get 3.5 times speed up over the bare JITted version. So if I use the Python version of that, is prime. You see that my pure Python took 84.6 milliseconds. I get a speed up just by adding the JIT, and I get another speed up adding the njit and making sure that I don't use things that are not compatible with the no Python mode. So I got about 20 times speed up over the normal, the bare Python function. Another way to have the bare Python function is this one. So is prime njitted or is prime jitted is a Numba compile function, but from it I can access the Python version. So if I have is prime jitted, there is a PyFunc object which I can use. Which is the same more or less as the one that I had in the beginning. So it's the Python function without the JIT. So even though I have the JITed object, I can still access the original Python function. So this is the way to do it. I run again here. So again, we see the difference in number. Any questions up to now?
Yes, can you repeat one more time what's the no Python is doing actually?
Yeah, so the no Python mode tries to compile without using Python object. Think of it like the Python we had yesterday that we slowly moved from complete Python mode to something that is native on the machine side. So in the no Python mode, these are no longer Python objects, but they are integers or floating points or NumPy arrays, as we're going to see.
Okay.
So that's why you get the speed up. So we started with the pure Python version, which is still accessible. We just added the JIT decorator without doing any change, but we get some speed up, but we're still using Python objects, although we are now using it at a lower level. And then we instruct Numba to drop completely the Python mode, which made us change some things that are not compatible with it, but we get the best speed up that we can take.
Thank you.
Okay, so now I added here one example with a cast equals true, where the compile function is cast. So if you had this outside of the Jupyter notebook, then the second time that you are going to run your function, your Python script, your JITed function will no longer be compiled, but it's going to the cast version is going to be used. So only the first time that you run your script, you're going to get the overhead. Here, you see that I use the cast version. So this is very good if you want to run a Python script many times, but pay the overhead of compilation only the first time that the compilation takes place. So take into account that this is different from the first compilation that we see here. And you see here that I run, it's already cast, so it doesn't compile. You might see some difference here from time to time because computation is very small. Let me add more stuff here. So you see now it's more or less the same. And even though I go and redefine the function, I don't pay the overhead of compilation. Although if I define this again with the njted one, because it's not cast, here I will pay also the compilation. So is this clear?
I have another question. Is there a way around of compiling it for the first time? Or no, you have to do it anyway?
Yes, there is a way to do it. And we will see it later, how you can compile ahead of time. So just a small comment since you asked. So here we pay compilation, the compilation overhead, because we haven't specified anything about what type of the arguments we are passing. So the first time, Number has to try and infer for us what is the type of all the arguments that we are passing and what's the return type. So we pay this compilation overhead. But there is a way over that, and we will see it later, on how we can specify from the beginning and make Number know that those are the types of our arguments, and it doesn't need to infer, and we don't need to pay the compilation overhead.
Okay, thank you.
Okay, so here I just added a vector triad benchmark to compare Python versus NumPy versus Number. So this is the original benchmark. It's just multiplying two vectors together and adding on a third one and assigning to a fourth vector. So we have 4 vectors. Here I do this using NumPy, just by using vectorization. And here I do it using Number and JIT. So it's the same. And directly you can see here that I can use NumPy arrays, the methods like shape, and Number is aware of the NumPy arrays. So let me run this. So you see that this computation in pure Python mode, it's 5 megaflops. In NumPy, it's 810, and in Number, it's even better. So let me run again. Let's increase our vector size. So you see Python is really slow, and this is the case because we have an explicit for loop. NumPy is much faster, but yet again, Number is even faster. So don't take this as a given for NumPy, because it really depends on the options that you have used to run NumPy. Because NumPy supports many different backends for doing the linear algebra. So depending on the backend that you are using, you may get different numbers. So you may be faster than Number. But you see that just by adding the Number and JIT for our computation, it's about 400 times faster than the Python one. So the megaflops here, I just calculate using the size of the vectors times the number of iterations times 2, and I divide by the elapsed time. So here is a simple timer that I just use, a Python timer. So any questions? So this was really trivial. And now we are going to address the question that you had before, how we can avoid paying the cost every time. So here, you see that, again, I have is prime and JIT integer. It's, again, a copy of the function of our initial function. And you see here, I have njit, but now I pass a list to it. So this list is more or less a list of function signatures that we want Number to support for this function. So we have a question. Let me see. please ask in the Q&A channel. But so the question is Numba compatible with the ufuncs of with the universal functions of NumPy? Yes, it's compatible, but then it will use the NumPy version of the vectorized version, and it will not compile the for loop by itself. So in some cases, more or less, giving it the for loop that you want to, giving it explicitly the for loop that you want to compile will be even faster. Please mute someone. If someone is not muted, please. Yeah. Okay, so it is compatible with ufunc, as I said, but sometimes it's we really need to express what we want to do so that it can compile even further for us. So returning to our example here, you can pass a list of function signatures, and see here you see I have one version which runs with an 64-bit integer and one version which runs with 32-bit integer. I compile, but now the difference is, let me run it. You see, I have no overhead for the compilation. Let me run again. No overhead for the compilation. The same time. So the compilation here took place at the time where I defined the function. The real difference here is that since we instructed Numba that these are the function signatures that we wanted to support, and it compiled ahead of time, now it will not support other types for this. So here you see that I can run as type int32, it supports that. But if I try to run, I convert this to float 64 and I try to run it, it says ambiguous overloading for function is prime and jittered eager. And it tells me that only this function signature I support. So you see the one version with the int64 returning a Boolean, and the one version with int32 returning a Boolean. So while if I comment this and recompile, the first time I will pay the compilation cost, but also now it supports float 64. Let me put it back. And you see, it doesn't support. So these are the two function signatures that it supports. And this, we can actually access them. The is prime eager has a list of Python signatures. You see, it tells us that it only supports int64 and int32. So no float here, which we could have added explicitly. Let me add it. I compile. And now you see that we have one more signature. So if you know exactly which signatures you want to support, this can help you in two ways. First, it helps you avoid the compilation cost, A second, it can be used as an extra check that when you try to run with an argument that is not supported, the type of the argument is not supported, then number will throw you an error instead of going and compiling something that we don't want to support. Any question up to now? Okay, so I assume that all of this was pretty straightforward. So let's continue along the lines of the Julia set that we calculated using Python yesterday. And today we are going to use the Mandelbrot set calculation as our benchmark to show how we can accelerate with number. So here I have the pure Python version, and it's a similar thing with the Julia sets. We have some complex numbers in the complex domain, and we do some calculation for each of the complex numbers that we have. And this calculation is independent for each of the pixels. So this is the Mandelbrot set. And you see that the pure Python version took 17.6 seconds. So let's go to our number calculation. So I have here the same, it's the same function, but I added ngit. So let me change this into the serial version first. So number ngit, I just added the ngit. So let me see. Yeah. So let me change this to range. So we'll see after. So you see that we went from 17.6 seconds to 0.3, more or less. Let's run again. Even faster, because now we didn't pay the cost of the compilation. So from 17 seconds to 100 milliseconds, to 0.1 seconds, more or less. And now you said you saw what I deleted here. So like we did with Python yesterday, yeah. So there's a question that says, is the compilation overhead reduced when using the ngit with the function signatures, more or less? Or it's simply done when running the cell with the function definition instead of when calling the function for the first time? So yes, so let me just return here. So here, that's why I have written eager compilation. So here the compilation is done when we define the function. It's not done the first time we call it, but we have to supply this so that that number has all the information to do the compilation for us before time. While in the second case that we don't have the function signature, the compilation has to be done when we first run it, because number has to find out what type of arguments we are using. So that's what we pay for more flexibility. So in this case, it's faster, yes, because we don't pay the compilation. So it's always a matter of what you want to do. So typically, when you develop a number function, you can go with the ng pay the compilation the first time, and then after you know which types of arguments you are going to use it, you can use directly the function signature and go with it. Okay, so will it run faster than when adding the function signature? No, it will not run faster because it will be the same thing with the just-in-time compilation. Just it knows ahead of time what signature to support. Okay, so you see that we had 107 milliseconds. So now I can add parallel equals true to the ng and run it. Again. So you see that it warns me the first time that it compiles. It says that the keyword argument parallel equals true was specified, but no transformation for parallel execution was possible. So Numba cannot auto-parallelize for us here, but I have to explicitly tell it, like Python, which loop to parallelize. So Numba has this p range, which is equivalent to the Python C range, p range, but it doesn't use OpenMP. It accelerates using the native code. So now I told it that I want to parallelize the external loop. I run. The first time I pay the overhead. The second time I use all my cores and I go to 10 milliseconds just by adding the parallelization. So it parallelizes the loop for me. Let's go again. First time I pay the overhead. Next time I don't pay it. And I'm fine. So here you could also add the signatures if you want to avoid. And I will show you later example how you can specify that the function is expecting more or less an array of type float or a 2D array. So it says CPU times 142, but the wall time is 10 milliseconds. So you see that it's much faster. Again, Numpy range. And the questions the question that comes here, and many times that I saw this example, is why don't we parallelize also the second loop here? And I try to do that. I get the same. But why is that? I parallelized also the second loop. So don't I get any speed up? So to see what actually is happening, I can tell this function to give me the parallel diagnostics. So you see here that I told it level 3 diagnostics to give me all the information. So here it gives me information on how it tried to parallelize the for loop. So Numba itself knows that by trying to parallelize both loops, then it will end up with more overhead for the parallelization than actually doing the actual work. So it says 5 is a parallel loop, but 4 here is rewritten as a serial loop. And it says before optimization, parallel, and after optimization, the second loop is serial. And it says that parallel region 5 had 0 loops fused and 1 loop serialized as part of the larger parallel loop 5. So the external parallel loop is the valid one, while 4 is converted to a serial one. So this has any effect, has no effect. And now parallel structure is already optimal. Questions? So although Numba needs some hint on what to parallelize, it's clever enough to tell us that you should not parallelize both of the loops, but you should parallelize only the external one for best performance. So there was a question before on whether Numba is aware of universal functions from NumPy. So these are functions that more or less apply to every element of a NumPy array. And instead of going with a for loop, then NumPy does it at the lower level, at the C level for us, but vectorized. So it's much faster than doing a for Python loop within Python. And here, I will show you how you can create your own U function, both using NumPy and using Numba. So let's assume that we want to create our own U function, which more or less supports taking 2 vectors, getting their sign, and then adding these signs together. So each element of the new vector is going to be the sign of the first one plus the sign of the second one. So here, this is the way to do it with NumPy. I get the sign of the first one, the sign of the second, using the universal NumPy functions and adding them. But NumPy allows you to create your own ufuncs outside of Numba. This is complete. This is pure NumPy, and by decorating a function with the vectorize. So here I supply NumPy the computation for a single element of my NumPy array, and then by decorating this, I can call it as if it was a ufunc embedded into NumPy. So if you see here, I have 2 NumPy arrays, 2 random arrays, and I use my sign function as if it was a NumPy ufunc. And then I have the last version with Numba, where I tell it to vectorize, and here I give the function signatures. I want to support floating point 64 numbers, 64-bit integers, and here is my return type, which is more or less the same as the arguments that I give. And I specify a target that I want it also to parallelize this. Let's define this and let's run. So the first version, the NumPy one, took 0.4 seconds. which is quite good. Then the ufunc from Python took a long time, and the number one was the faster. So let's see what's happening. Although I specified here NP vectorized, this is still a Python code. So NumPy cannot compile it for you at the C level, but it just makes it a convenient way to specify your ufunc. But again, this is going to be in the Python level. So it's not going to be fast. It will just be convenient. While Numba can do it for you and compile it natively. So let's run now without the overhead of the compilation. So you see. Okay, so there's a question about what is the difference between hold time, user time, and sys time. So the user time is actually the time that the CPU is using to run work for us as a user. The sys is the time that it spends asking stuff from the operating system, and the total is more or less the sum of these two. So the hold time actually is the time that you would see on an actual clock. So it's the time that it has passed as if you had a clock and you timed the execution yourself. So it's the total time. And the user time here is much larger, you see, because it takes into account that this executed in many processors. So you see that the hold time is 40 milliseconds, while the actual computation time is much larger because it includes all the computation that took place in all the processor. Okay, so there are two questions. Let me answer both. Why there are so many signatures in this line? So there are not many signatures. There are two signatures. So the first one is, you see, this float 64 is about A. The second float 64 is about B. And the first float 64 here is about the return type of the actual computation of the actual ufunc. So this is only two function signatures, but I have to specify all the different arguments. And the second question, how can the hold time be lower than the CPU time? It's the same as here. So the CPU time is actually the time that its CPU took multiplied by the number of CPUs roughly. So it's the whole time that the CPUs did computation. So suppose that you have two CPUs and one took 50 milliseconds and the other one took 40 milliseconds. Your CPU times will be the total, which is 90 milliseconds, but then your hold time will be the larger of these. So the hold time is actually the time that you have to wait for the computation. And so this is the difference between the CPU time and the hold time. So there's a question. Please ask on the Q&A. How do you pre-compile if the argument of the function are a NumPy array or list? So I will show you later how this is done. But now that we know how to do vectorization, we can even vectorize our isPrime. So now we have a vectorized version of isPrime, and we can have a NumPy array and pass it directly to it. So we don't have to do a for loop, nothing. We just pass this. So here I test 100,000 numbers, whether they are prime, and I can even target parallel execution. So you see here the wall time, and when it runs parallel, it's much faster. So that's the difference. You see, when you run on a single CPU core, the wall time equals the CPU time, while when it's parallelized, they are no longer equal. And by using this convenience, now we can use all the good stuff that NumPy provides for us. So here I print the largest number from 1 million to 10 million. And you can do it easily using the parallelized version of your is prime. So is this clear? So what's the difference between number vectorized and number ngit? So the vectorized is used to create NumPy ufuncs on the fly. So this means that you don't have to, here, if this was an ngit, then I would have to do a for loop for the whole array that I would pass. While here, I just specify the computation that has to take place for a single element, and by using the NumPy vectorize, make it accessible for NumPy arrays. So this function can now be used with NumPy arrays directly. So if I didn't have the vectorize here, for example, the Zine, I would have to go with either use again the NP Zine here or use the for loop for each element of A and B. The vectorize has the meaning that you only supply the computation that has to take place for a single element, and this computation is then applied to all the elements of the NumPy array that you are passing. And this is going to be true also for 2D arrays, as long as the arrays are of the same shape, these two arrays. Okay, if there are no further questions on that, I cannot open. So there's a question that does NP vectorized help anytime in practice? As I said, the NP vectorized is just a convenience function. So it's not as fast as the vectorized functions that NumPy provides. So here is where NumPy comes in, and it can compile at a native level for you. So NP vectorized is just a convenience, and it's better to use the vectorized versions of NumPy directly. And if you have something really complicated that's no ufunc covers you, then here is when you have to start exploring something like number. So there's a question like, why no Python equals true no longer supports this thing here? So as we said before, if I try to compile this, I get an error that failed in no Python mode. So this here is actually something that is pure Python, so it's a string formatting thing. I can try to do it otherwise with an F string or whatever, but because it's a Python object, more or less, it's a Pythonic way of doing things. In no Python mode, Numba cannot do that because it wants somehow to compile at a lower level using bare primitives. So this is not supported. That's why I had to change to something which is a pure string, more or less, which it can recognize. So yes, that's why we changed as a pure string. It can be a pure string, or you can change it to like return something like false on its own, or whatever is more convenient. But yes, you cannot use Python objects if you want to get the full speed up. Otherwise, you can go with no Python equals false, or don't use anything related to ngit, and continue with the Python objects. Okay, so let's go quickly to the Numba stencil now. I want to show you. So let me close this. And okay. So for those of you who are not aware of stencils, stencils are typical computational kernels that occur in scientific computing, especially in the field of differential and partial differential equations, when we're using finite differences to solve these equations. So Numba provides a convenience function, which is called Stencil, to assist with this kind of computation. So here we have the partial differential equations for heat, our boundary conditions and our initial conditions. And you discretize this heat equation by substituting the differentials here with differences. So more or less, you take your 1D domain and you split it in smaller elements with delta x distance between them, and then you substitute its difference with the values of the neighborhood points. And by combining the values of the neighborhood points, you approximate the differential. So here you see for point UI here, I have the neighbor values like UI +1 and UI -1 on the right and on the left, and I will use this to approximate my differences here. So the differential equation here is replaced by differences. So here I have my equation, and I end up with this computation, which tells me that the value of the temperature at point I and at time n+1 is calculated from the value of the temperature at that point in the previous time step, plus some values, some neighborhood values of the previous time step. So now, how can we do this with Numba? I create this. So you see here, you always have to specify that you want the correct kernel. So I change my kernel here, and I run, and now I'm fine. Okay, so there's a question of whether we should post the answers to these questions. Yes, so in the during the break, I will add the answers to the questions to each one of the questions below, so that you have it also in a written form. So let's continue. So here are some simple computation to define my 1D domain. And here is the stencil. So in number, I just have to specify more or less the relation of the stencil. Let me show you here how this relates to that. So here is more or less the stencil computation. So assuming that we are at point I, which is the point 0, for example, we specify that the next value is the value at 0 plus f times the value on my right, which is x1, minus 2 times the value, my own value, plus the value on the left. So I just specify the relation for the stencil. And then I run my simulation for as many time steps as I want. And here you see that I have added the NGIT and I used the stencil computation. So this is how it looks like. So this is the temperature at time 0, and you see that we run the calculation for many time steps, and in this case for 100 time steps. No, it's 10,000 time steps, but up to time 100. And you see how the temperature has spread throughout our domain. So again, the stencil is just a convenience, but then we have to use the NGIT for our computation. So here is the for loop where I just run for the number of time steps. Keep in mind that here I have given the initial boundary conditions, and I proceeded with the simulation to run for the next time steps. So this is just the convenience. Otherwise, you would have to do a for loop for all the points on your 1D domain, and Numba offers this convenience for you, which can be used from NGIT directly. Do you have any question on that? For those of you who are not familiar with stencils, again, it's a typical computational pattern where you combine some value at some point on a 1D, 2D, 3D grid with some of your neighboring values and arrive at a result for each of the grid points. So maybe this is even clearer in 2D, although the simulation is more complicated because we are in 2D. Now we have a point Uij, and now the stencil includes both elements at the horizontal axis and both the neighboring elements at the vertical axis. So this element here is affected by its neighbor points. So this is a 5-point stencil, and there are other types of stencil that include more or less of the neighbor values. But again, the computation is easily expressed with Numba stencil. So this is the computation, and this is what we actually want here. So this is, I cannot highlight it correctly, but this is the computation that we want to take place, and it includes all the neighboring points. And now I have 2D arrays, and you see here that I use x00, x minus 1, 0, x00 again, x1, 0, which are the points at the horizontal axis, and then we have the points at the vertical axis. So I can run again the simulation. Again, I use the ngit here. And now we have a 2D pattern. You see here the initial temperature from a bird's eye view. And here you see how it's spread out when the computation proceeded. So it's just a convenience function, but then it can be used directly with ngit to accelerate our computation. Okay, so how does Numba Stencil treat the boundary condition? So that's a very good question. So for the moment, the caveat is that it assumes that the boundary conditions are either a zero value, or you can specify a constant value. There is another argument that you can specify with some kind of function how to treat the boundary conditions, but it's not clear yet how much this is supported. So that's why here I had to go and specify the values of the boundary as 0, and then Numba will handle the boundary conditions for you, and it will find out which are your boundaries based on the shapes of the arrays. So I have a small question so because the x minus 1 point is changed at every time step. So you see here that all my values on the right-hand side refer to the previous time step. And the value on the left-hand side is referring to the next time step. So here, what I did was I ran the for loop. I used my values here, x, and when the computation has finished, the new values are copied back and replace the old ones. So all the previous values are used to compute the new ones, but there is no effect since this is an explicit finite difference, which means that everything from our previous time step is on the right-hand side, and explicitly we can calculate the values for the next time step. And there's another question, how I specified the boundary conditions at the first case. So here I didn't have to specify anything because I declared everything as 0, and which I could do the same, but for here, but the domain is more complicated. So I had to go and specify this. And here I specified the values for some of the grid points of the domain. So you see here, all the others were 0. While in the other case, I had to go, because the computation is more complicated, I had to explicitly specify the values at the boundary points. So let me go quickly at the final thing that I have to show you for Numba. So this is optional, and I'm just adding it here so that you have you have it for your reference. So we saw the NP vectorize, but there's also the GU vectorize, which is for generalized vectorization in NumPy. And this is a way that, if you're not familiar with generalized U vectors, so just have it here for your reference. So the generalized U funcs is a way to specify a computation, to define a computation when arrays with different shapes are given to the function. So here I have the GU vectorize, where I have my function signature. This is the way to specify an array. This is float with 8 bytes, and here I specify that it's an array. And here is a way to specify, it's like the einsum convention on how you have to treat the GU vectorization. So here I specify how I want to treat a number as a how I add a number to some vector. So you see here I have a y0, and the difference here is that the GU vectorize has both the input and the output as the argument. So the last value is the output, the Z, and the two of them are the inputs. So I specify this, and then I can use vec_add_const and add a constant value to a vector. So here the GU vectorize is there to support different shapes of matrices. So you see here I had a vector with length 10, and with the GU vectorize, I can specify how my computation is going to take place with different shapes. And here I can do it with a 2D matrix now, and as a constant, a 2D matrix and a vector. And here I have for your reference how you do matrix vector multiplication in a vectorized way. So here you see that my input is the first one is a 2D array, the second one is a 1D array, and the third one is a 1D array again. So I go from an m times n matrix and an n vector to an m-dimensional vector. So this is the typical matrix vector multiplication. I can specify it, and it works. And even more complicated, the matrix-matrix multiplication. So you see now that all my arrays are 2D, and I have m by n and n by k array, and my result is the number of rows of the first matrix and the number of columns, the second one. So the first argument is the signature, and the second one is how we want the shapes to be manipulated, how this behavior we want it to be. And I added this for your convenience, the documentation for NumPy-GU vectorize, and I used the first using my mat mule that I created, and the second one is the matrix multiplication from NumPy itself. So this is for your reference. If you want to go even further than this, the normal GU vector, the normal U funcs, to go to generalized U funcs, which support computations between NumPy arrays of different shapes, different but still compatible. So in here I could not matrix vector multiply with a vector which doesn't have the same dimension as the number of columns here. So it will throw an error if you try to do that. So if I had this here, for example, it says that input operand 1 has a mismatch in its core dimension. So size 4 is different from 3. So I know this went a little bit quick here, but I just added this for your reference in case you want to see some examples for the GU vectorize. The GU functions are a Numpy feature, and Numba also provides this for you so that you can create a GU vectorized GU func on the fly and compile it natively. So we can have a break up to 10:35. Of course, feel free to ask questions. So the question is it possible to use Stencil to formulate implicit schemes or more complicated problems that require, say, adaptive variable time steps? In this case, you cannot use, I suppose, Stencil, which is just a convenience, but then you will have to go and write all the computations by yourself, because otherwise, if you have different time steps, then the constants of your scheme change in every time step. So the Stencil is not aware of that, and you cannot do it. Maybe you can. I have not tried, but as you see, even if you try to use if you want to use more complicated boundary conditions, then the Stencil convenience is limiting you. So there's another question for the example of, and okay, let me see. Okay, so the question is, I have this, the NP range 27, and I reshape it to a 3 by 3 by 3 array. And then I have a simple NP array here, which is one dimensional. Then here we have created a GU function that treats only 2D arrays and then 1D arrays and gives us a 1D array. What happens here? So here I have a 3D array. You see, I have a 3 by 3 by 3 and a 1D array. So the power of the GU vectorization is that it allows you to use the broadcasting rules of Numpy. So here, a 3 by 3 by 3 array is compatible with a 1D vector. 3. So what is going to happen is that we're going to have a vector multiply each of these one of these 2D arrays here, and we'll get more or less 3 different vectors which contains the values that we want. So here we have 1, 2, 3. If we multiply by this row vector here, we will get the 8. If we multiply by the second vector here, we will get 26. If we multiply with the third vector here, we will get 44. And then we continue with the second array, the second matrix here. Again, we get the vector, first row, 9, 10, 11 with 1, 2, 3, 62. Second row will go and will give us a result of 80. And the third one, this row here multiplied by this vector will give us 98. Now the third matrix here. So the good thing with the GU vectorize is that you specify what happens with the dimensions, what you want to do with a 2D by 1D, but this enables you to use the broadcasting that NumPy provides. So if you look at the broadcasting rules and see also the GU vectorization computation, you will understand what is going to happen. Was this clear? So there's another question. Okay. So this is a question about the NumPy stencil. So what is happening here? So here, I more or less specify some initial conditions for some values of the temperature. So here you see that I specified only for these values here on the x-axis. So I take the indexes from half of my beginning from the mid of my domain up to the mid of my domain plus a tenth of the length. So you see here that this is more or less a tenth of the whole length, and we begin from the mid of the grid. So it was just a way to specify some initial values close to the mid of the domain to see how this temperature spreads when time goes on. So it is just a way to specify the initial conditions. Okay, so since this went a little bit longer, let's do a break up to 10:40 and come back. Okay.
Yeah, it looks good. Perfect.
Okay. Okay, so now I will start with this quick introduction to the GPU architecture, because we are going to dedicate the rest of the day to how to use Python to harness the power of GPUs. And I'm going to start by introducing the GPU architecture for those who are not familiar with it. And this presentation, and then the next notebooks that we are going to use for Numba and how to use it to accelerate using Cuda to harness the GPUs, was prepared by my colleague, Vasilios Karakassis, for some previous rounds of the course. So let's get into it quickly. So I'm going to briefly summarize here what we're going to talk about. I'm going to talk about the difference between GPU and CPU, the difference in execution model and how the execution model in Cuda works, and also the difference in the memory model, because the GPUs have dedicated memory, so we have to take care of the memory handling of the GPU ourselves. And then we go on with the notebooks on before up to lunchtime and the 1 hour after lunch, onto how we can use Numba to generate CUDA code for our applications and accelerate them with the GPUs. So this is the most important slide, and it shows the main difference between the philosophy in the design of a CPU compared to a GPU. So you see here on your right top, this is how the area of the die of the CPU looks like. It's a simplistic view. And compare this to the picture on the bottom, which is referring to the GPU. So our CPUs are optimized for low latency access to cache data sets. So you see here that much of the area is dedicated to cache, while our logic and the control dedicate a small portion of the CPU die. And it's optimized also for out of order and speculative execution. Contrast that to the GPU here, you see with green how much of the area of the chip is dedicated to computation. And the GPU tolerates the memory latency, and it does so by introducing massively parallelism computation but via much more transistors which are dedicated to actual computation. So you see here, we have some very small caches, while above a very large area of the CPU is dedicated to cache and control. GPUs are basically throughput devices. As I said before, CPU cores are optimized to minimize latency between operations, while GPUs minimize latency by scheduling multiple thread bundles which in NVIDIA Cuda terms are called warps. So you see here the difference. We have 31, which does some processing, it waits, it does a context switch, and then a next thread runs, and another processing takes place, some waiting, another context switch. While in the GPU, you see all the different warps that are scheduled from execution at the streaming multiprocessor, which results in the high throughput. And this is how GPU hides and tolerates latency compared to the CPU. And current applications are not designed for many cores. So we have to expose ourselves and develop this fine-grained parallelism in our applications so that we can take advantage of them. And new programming models were required for this. New algorithms are required many times. So an algorithm that is optimized for CPU execution in many cases is not suitable for taking into advantage GPU and its programming model. And the existing models and the existing codes have either to be rewritten or refactored in a way that takes into account these peculiarities of the GPU devices. We'll see how we do that via Number, and later in the afternoon session, in the late afternoon session, how we do this more easily and more on a high level using CuPy. So because of the way that an application is programmed to take advantage, to squeeze out every last bit of performance from the CPU, users are not getting the most out of the allocations when GPUs are used. And in the future, the amount of parallelism is going to increase even more. So that's why we have to change our models for our existing codes to be future-proof in order to take into account this increased parallelism. So this is a picture of the architecture of the GPUs that pitch-dined our main system has on CSCS. And these are the ones that we are going to use with Number and CuPy later on. And you see here the streaming processors and all the different computational units in green and yellow. So much of the area of the device is meant for processing. So the streaming multiprocessor architecture that the NVIDIA GPUs have, we have many lightweight single-threaded cores. There are 64 in the P100 device, and we have synchronous executions of groups of 32 threads, and each 32 threads constitute a warp, and all 32 threads execute more or less the same instruction synchronously. We have a very large register file partition per core. You see here the register file. And then we have the warp scheduler, which picks the next warp that is ready for execution and submits it for execution. And the warp switching is very fast compared to the context switch that is happening on the CPU. Also, we have different kind of memories on GPU, and we have also the user-managed shared fast memory that we are going to use also in our examples to accelerate more our applications. the execution model now. So the GPU cannot execute code on its own like the CPU does. So the host, which is more or less the CPU, sets up and launches the kernels on the GPU. We will see what the kernels are for those of you who are not familiar with them. So the CPU sets up the kernel and it sends it to the GPU for execution. Also, the CPU has to manage the memory allocation and the memory transfers on the GPU. So currently, we have the GPUs that have a separate memory from the CPU, and therefore this memory has to be handled differently and explicitly by us and transfer all the memory allocations, all the memory allocation that we do on the CPU and on the GPU has to be managed explicitly by us. So we will see that the arrays that we allocate on the CPU have to be transferred on the GPU. We do the computations there, and then we transfer the results back to the CPU so that we can use them. Also, there is the concept of unified memory between CPU and GPU, where the virtual address space is shared between the host and the GPU, and the Cuda driver more or less takes care of this allocation and device transfer of the CPU, what we have allocated on the CPU to the GPU. So it was introduced in the Kepler architecture, and it was significantly improved with Pascal that we have now on peacetime. And again, the execution model, how we take control of this massive parallelism of the GPUs. An application launches kernel, which the host sends to the GPUs to be executed there. And each kernel comprises several blocks or gangs of threads. A thread block can run on a single SM, and multiple thread blocks are launched to execute the kernel, and multiple of them can be accommodated by a single streaming multiprocessor, taking into account that there are enough register, enough shared memory, and we don't reach the active warm hardware limits on the SM. And warps or any active block may be scheduled to run on the SM cores. So this is just the theoretical stuff. We'll see how this is going to be used when we use Cuda from Numpy. So here we have the streaming multiprocessor, which have shared memory, a register file, and a warp scheduler. And here on the left, we have the kernel blocks, which are then sent on the SMs, and the warp scheduler schedule each block for execution on the streaming multiprocessor. You see here how the different streaming multiprocessors schedule the kernel blocks for execution. And as I said before, a single warp, the threads of a warp execute a single instruction, and they execute it, all of them together. So if there is some branch, so some threads of the warp need to execute a different command, then all the threads try to execute this command, while the threads that should not execute it are deactivated. You see here that A and B are going to be executed by the threads 0 to 3, while the others are deactivated. While in the next step, all the other threads are activated now, and the first ones are deactivated, and we execute the C command here. So each thread can take a different path, but since we have the branching here and the warp execute a single command synchronously among all its threads. Some threads are deactivated. The threads that are active execute the instruction, and then the threads that are not active don't do anything, and the other threads execute the command that we need. The implications of this is that we have to exploit as much parallelism as we can to cover these latencies and that the GPU tolerates, and enough works must be available to schedule all these different kernel blocks at the same time. Global synchronization is not possible because all the blocks of the kernel do not run at the same time, so you cannot synchronize between them. And synchronization is only possible within the threads of the same block. And as we saw before, if a program's control flow diverges within the same work, we have redundant execution because both branches need to be executed by the work. Now, the memory hierarchy. The memory latency is handled, is hidden by the very high bandwidth memory that the global memory has. On P100, we have a theoretical peak bandwidth of 732 gigabytes per second, and it's accessible for all thread blocks. It's persistent across kernel invocations, and memory accesses of work threads are coalesced into one or two memory transactions if they are properly aligned and regular. We'll see how this affects our code later. And then we have the shared memory, which is shared among the threads of a single thread block, one cycle access latency, if work threads access different location. It's software or hardware managed. We'll see how we will manage it via number. And we don't have cache coherency across streaming multiprocessor and no sequential consistency. We have to use synchronization primitives to enforce that. Other type of memories are the local memory, which this is not visible to the programmer, but this is where the compiler places the automatic variables. We have the constant memory, which is a cached part of the global memory to store constant values, which is visible to the programmer. And then we have texture and surface memory, which comprise a cached part of the global memory optimized for 2D accesses. Now, how do we take advantage of the GPUs? I said in the beginning that different programming models have to be employed for this. And we have the low-level native APIs where you need to go at the lowest level with Cuda C++ for NVIDIA GPUs and ROCm for AMD GPUs. We can go at higher level using directives such as OpenMP 4.5, which support accelerators, and OpenACC. We can use higher level libraries which already support GPU acceleration like Focus. And then here is where this course comes. We have higher level languages such as Python, where we can accelerate our code via Numpy and CuPy that we'll see today. But there are other alternatives like PyCuda and PyOpenShare. So thank you for your attention on this brief slides introduction. So is there a question on this? Okay, so I suppose that you want to see something practical now. So I'll stop sharing the slides. You can find the slides at the Git repository, by the way. So let me start sharing now my Jupyter notebook. Okay. So can you see it?
Yeah.
So now we will go Python HPC, Numba, Cuda, and we will go at the first slides, Numba, Cuda basics. Let me know if something is not clear or if it's not visible. The size, okay. Rafael, is the size okay?
I think it's fine. If you want, you can go a bit higher, but
Like that?
yeah, that's better. Yeah.
Okay. So now we are getting our hands dirty. How to use Numba for GPUs. Of course, the first thing I have to do is go select the correct kernel, which includes Numba. Before we saw Numba and how we can use it to accelerate CPU code by letting Numba compile the functions that are critical and compute intensive for us to native code. And now we're going to use it to generate Cuda. Also, ROCm is supported, but on Pitstein we have NVIDIA GPUs, so we will focus on the Cuda capabilities of Numba. There is almost a one-to-one mapping from the Numba high-level Python abstractions and the different Cuda constructs for those of you who are familiar with Cuda C and C++. So you can explicitly allocate host device memory and transfer arrays to the GPU directly, and we'll see how we do that. And these notebooks that we are going to use will give you an understanding on how to write basic Cuda kernels using Numba. We will cover basic Cuda programming principles, which are a little bit complicated if it's your first time programming a GPU, but they are enough to kickstart you in GPU programming. So, in more detail, we will cover this. We will write a GPU kernel. We will move data from our host to the GPU. We will spawn a GPU kernel. We will profile a GPU kernel. We will optimize memory access. And this is where it gets critical to see how the memory is handled differently in GPUs. And what was initially optimized for CPUs might not work for GPUs. And then we will show how you can take advantage of shared memory, but we will not cover Cuda streams, which is some more advanced topic, but you can always use Cuda streams from within Numba. So the first thing that we need to do when we have a Numba installed is to make sure that the Numba works fine and it recognizes our GPU. So I said yesterday that we can run shell commands from within a Jupyter notebook using this exclamation mark here. And here I run Numba S. So it will give me the system info here. It gives me the Haswell information, and then this is what we want in our case. Cuda information, Cuda driver, Cuda runtime version and compute capability. You see here, we have one GPU, the Tesla P100 with 16 gigabytes, and it tells us that it is supported more or less for Cuda. So everything here is okay. Then it says some NumPy information, and then the install packages on the Python side. But the important part for us is the Cuda information here. So now that we are sure that our device is recognized and supported, let's go down to write our first kernel. Also here, we don't need to set our Cuda home since everything works by default. So is everything following with me here? We are writing the first kernel. Go to the Q&A and see, and don't see any questions. So I suppose that everyone is following here. So let's start with our first kernel. So here we want to make a simple kernel that in Cuda terminology, the kernel is actually a function that is going to do the actual work on the GPU. And this kernel will be used to add two vectors. And this is equivalent more or less to something that we did before with the vectorization. So we want to write a kernel and write more or less the computation that takes place for each of the elements of this vector. So this is the actual computation. Of course, we make sure that our index is not larger than the shape of the vector here, because this is not handled explicitly by Cuda. And how do we differentiate now, and how do we know the index in where each thread is going to run, which vector element each thread is going to do the computation for? So here we use the Cuda grid function. We will see what this does in the moment, but bear with me. And in order to create the Cuda kernel in the first place, we have to use the Cuda JIT decorator now from Numpy. So let's run this. So a Cuda kernel is a Python function which does not return a value. So you see here, we don't return anything, but both input and output is passed as the arguments for the kernel. So Z is our output and X and Y is our input. So as I said, the kernel specifies the work that is going to be done by a single GPU thread. And because of the massive parallelism on the GPU, a GPU thread gets a tiny portion of work. And in our case here, a thread will only going to compute the sum of a single element of the output vectors. And this we can do it easily because each element is independent from each other. And we can create safely as many threads as the element of the target vector and spawn them. We'll see how we do this later. So you saw from the introduction that threads in the GPU are organized as in groups called blocks. If someone is not muted, please mute. So we have again the Cuda blocks, which consist of many threads. And here is how the vector looks like. So imagine that you have a 24 length vector. So here we have 8 threads on block 0, 8 threads on block 1, and 8 threads on block 2. So each thread of each block will take care of a single element of the vector. And in order to obtain the thread number, the global thread number, because you see here that this is thread 0, but for block 1, and in order to differentiate and get a unique index, this is what we need to use. So here, this is the block size, which in our case is 8. IB is the index of the block, and ithread is the thread index, but within the block. So imagine that we want to access the 10th element of the vector. This is going to be assigned to the first block and thread 2 of the first block. So here we have IB, which is 1, times the size, which is 8, and I2, which is 2, so we'll get 10. So the 10th index of the vector will be assigned to thread 2 of block 1. And this is the relation that is going to give us this. So I, which is the global index, is equal to the block ID on the x-axis. We have a single dimension for our blocks now. We'll see later how we go in 2 dimension. The block dimension on the x-axis and the thread ID on the the thread index on the x-axis. And because this computation is very common, Numpy provides the convenience function, Cuda grid, and this is the grid. The one here tells it to give us the global thread index on the grid on the first dimension. So here is how we take the index. As I said, here we have to explicitly make sure that threads with a global index greater than the number of the shape of the array, of the length of the array, don't do anything, because otherwise we will try to access memory outside of our array, and we don't want that. And this is the actual computation that's going to take place. So we express the computation for a single element of the vector, and we differentiate this computation on the different elements by taking the index as the global thread ID. So let me know if you have any questions up to now. Let me just repeat this so we are on the same page. This is our kernel. It does not return anything. Inputs and outputs go as arguments here in the kernel. Here, this is going to be executed by each thread of each block. To differentiate which element each thread should take, we retrieve the index by using this convenience function that Numpy provides. And now the thread knows which element to do useful work for. Here is our check that we are not outside of the bounds of the array. And here is the useful computation that is going to take place. So it's similar to the Numpy ufuncs. If you see it on a high level, we just specify the computation for the single element. So we have to make sure, the question is, why do we need this check? So the Cuda kernel, unlike what we had before with the ufuncs, does not know explicitly the shape of the array that we are going to pass. So we have to check, and if a thread number is larger than the size of the array, we don't want it to do anything. And this is needed because typically the number of threads that we are going to spawn do not match exactly the shape of the array. So we might launch 1024 threads for an array of 1000. So some of the threads have to make sure that they don't try to access elements outside of the boundaries of the array. So we have to make this check explicitly. So I see another question coming. As I said, I will answer to all these questions when we end today's presentation, so that you have it for your convenience in written form as well. So when would you need, the question is, when would you need a Cuda grid with dimension more than 1 here? So in general, you can launch thread blocks with shapes, with different shapes. So we don't need to have a thread block which is 1D. For other computations, like the matrix vector multiplications that we are going to see, we can use a 2D block. So in that case, we would need to access I and J, for example, which would be the row, which would be the thread global index at on the x-axis and on the y-axis. So for the y-axis, in that case, we would need grid 2, and for the z-axis, if we had a 3D thread block, we would need grid with 3 here. So you're not confined to a 1D thread block. You can launch multi-dimensional thread blocks. So we have 2 questions. So the first question is that what's the difference and the benefits of n larger than 1? So this is clearly the case. The difference is related to your to the application that you are going to use. So for a 2D grid, for example, a 2D block makes more sense because then your indexing is much easier. So maybe also my colleagues can make it more clear here.
Yeah,
but
I could add that the performance doesn't, it's really for convenience. It shouldn't affect the performance because the performance is affected by different factors such as your memory layout and practically how you're accessing your memory. And Theo will go through more examples on showing that. So it's just for convenience practically. You could always go with 1-dimensional grid and just do the calculation yourself of where you're gonna land.
But in that case, you would have, for example, for the 2D applications, imagine that you have an image, then you would have to map everything to a single dimension. So in that case, it is easier to work with the 2D grid because it makes your computation for the indexes much easier.
Yeah, exactly.
Okay, so now there is another question. What happens if the array is bigger than the largest number of threads that can be run at the same time? So if the array is bigger, then the computation is, and we launch less threads than the shape of the array, then all the threads are going to do useful work, but we are not going to cover the entire shape of the array. So we can have an array that is 2000 and launch 1024 threads. So the computation will take place only for the first elements of the array or whatever we do. So we're not able to cover unless we want to do multiple computations per index. So you might want to do to have each thread take the computation for 2 or 3 or more elements of the array. Then you can go with less threads than the elements of the array, but you have to explicitly know that beforehand.
Yes.
We will see how we handle this case, because sometimes the limits of the number of threads that we have is less than the actual size of the array. So in that case, we have to take into account and make the threads do more work for more indexes. So could multiple warps running at the same time, or only one warp running while all the rest threads waiting? So multiple warps from different thread blocks can run at the same time, but the threads of the single warp must run the same command, the same instruction, all of them. So if there is a branch, some of the threads of the warp are going to be inactive. The actual active threads will do the useful work, and in the next step, the first threads are going to be inactive, and the other threads are going to execute the second branch or the third branch. Okay, so we said that the memory on the GPU is separate from the memory on the host. So we have to do the transfer from the CPU to the GPU ourselves. But even if we use unified memory, Cuda will do that as a convenience for us. But this transfer always takes place. So here I will start by importing Numpy. I will create a random engine from Numpy that will give us the randomness. And from this, I will generate 2 random vectors. So for our reference, I will compute the result using Numpy. So now here is how we are going to transfer the vectors to the GPU. Now dx is the x vector, the x vector's twin, but on the GPU side, and the same goes with the dx dy vector. So Cuda to device will do the transfer for us. So now we have 2 vectors allocated on the GPUs, which have the same content as the x and y. So dx, if we look at it, is now a device and the array, while x is a Numpy array. So the dx is x's twin, but on the device. And the z array, which is the one that will contain our results, has to be allocated also explicitly by us. So because this is going to be populated by the kernel, more or less, we just allocate using this convenience function from Numba, device array like x. So this will create an array with the same shape, but without some explicit values inside, and it will be allocated directly on the GPU. Now, we have to invoke somehow the Cuda kernel. We have to let the host know how it's going to launch the kernel on the GPU. So we have to pick a right size for the block for that, which typically is not always straightforward, but usually values from 64 to 256, depending also on the application, are fine. And block size in our case here is 128. So the number of blocks that we are going to use is going to be the size of the vectors divided by the size of the vectors divided by the size of the block. So in this case, if the block size is not a multiple of the size of the vector, we have to make sure to add one more block onto that. So here I didn't specify that. So in this case, print num blocks. So we are going to use 8 blocks of 128 threads, and we are ready to launch our kernel. So this is the way we do it from Numba. For those of you who are familiar with Cuda, from C, there is the syntax which uses this notation to specify more or less the number of blocks and block size. Here, we use the square brackets. And here we don't return anything because the kernel does not return anything, and both our inputs and outputs go into the kernel parameters. You see here, now I use the device arrays. Let's execute the kernel. And here you see that it gives us a warning about the grid size that we have used. And here the grid size of 8 is very small, and it tells us that the GPU will be underutilized. So Numba is clever enough to tell us that for such a small vector, like the GPU is going to be underutilized. Now that our kernel has done our computation, we have to explicitly copy the results back to host. So here, DZ is our array, our vector that contains the results, and we have to transfer it back. And this is done by the copy to host function. And this returns a host array with the contents of the GPU array. And we have to make sure that our computation is correct and that the results are close together, and the zref and the result indeed are close, so the computation was correct. So for completeness, so that you have everything in a single cell, have everything together here. So here we have 1000. And in this case, this is not a multiple of the block size. So we will launch 8 blocks, more or less, but some of the threads of the last block are not going to do useful work. Let's run that. Again, we get the performance, and we make sure that everything is close. We can execute something larger. And again, everything is close. Any question up to now? So we can see also the GPU memory here. The occupation is really small. Let's go for a larger one. You see here that the GPU memory has gone up because of the allocation that was done on the GPU. So I see a question coming. Yeah, so the question is, I'm not sure I understand the warning that Numba gives us, which says that the grid size is smaller than the SM count. So let's go back here. So here we have the block size, 128. So we are going to launch block size 128, and how many blocks we have. Sorry. So we are going to launch 8 blocks, and each one of them has 128 threads. So this tells us that the grid size, which is 8, which is the number of blocks, is less than 2 times the SM, which is more or less 2 times the number of steaming multiprocessors. So this will go to only a small number of steaming multiprocessor. So a large portion of our GPU is going to be underutilized. Let's go to something larger. And now you see that we have 7,000 blocks and the warning goes away. So now all the GPU will have useful work to do because all the SMs are going to be occupied. So the cube grid here, the Cuda grid here, is only to get the index of the global thread index to know which element to do the computation for. So in this case, I will be from 1 to 7,813 times 128. So the number of blocks, the total number of threads will be this one. So you see, it's more than the number of elements of the vector. So that's why we need this here. Okay. So there's a question that goes like, but I ran this computation with that size here and an error was raised. So let's see what the error is. Okay, so in this case, the Cuda error out of memory. So you see here that more or less that size of the vector tried to occupy more than the GPU can handle. So let's look here. So here we have a memory of 8 GB, which is for the host. And now we have a GPU memory of 550. If we double that, the GPU memory that we ask for the GPU is a little bit more than 1 GB. So because the memory of the host is different from the memory of the GPU, we have to take also this into account. We cannot allocate more than the GPU can handle. In that case, what we would have to do would be to split the computation so that we send chunks that can be allocated on the GPU and then copy back to the host on the right location. If you want to run a computation that needs more memory than the GPU has. So more or less, it tells you that I cannot do this allocation. Even if you try to do some allocation, some very large allocation, and you exceed the memory of the host, then the host will complain before you can actually arrive at the device allocation. So typically, the memory that is available on the host is larger than the GPU one. So this is one other limitation that you have to take into account when programming for GPUs. So we can run with a different block size here, and you see how it changes. Can run with 512, 1014, and if I try to do that, then it complains. Cuda error invalid value. So there's a limit to the actual number, to the actual size of the block size that we can give. This depends on the CUDA architecture, I think. But in general, even the maximum size we don't use. And this is because when we increase the maximum block size, we limit the number of concurrent blocks of threads that can run together. So it's always a balance. You have to balance according to your application, the number of threads and the number of blocks that you are going to use. Any question? Okay, so since you don't have question, you can try this for 10 minutes for yourself and tell me what you see. So try to time this. You can time it with one repetition, one time. And then you can try with this and use different sizes for the vector and see how this compares to time it x plus y, which is going to be executed on Numpy. Just adding here so you can see. Here what is done. So for your information, try to put all this in another cell so you don't really find the kernel. So do all this so you don't have to redefine the kernel every time and try to time it. So N1, R1, and yeah. So the same goes with the CUDA version of JIT and like the CPU version of it. every time, if we don't specify, and we'll see how we do that, explicitly the signature of what we want to support, the first time that Numba sees this, it will try to compile it. So it will have an overhead. So try to run this and also change the number of repetitions and let me know what your findings are. So there's a question.
Yeah, I have answered that in the chat. So it's whether we have to worry about cache hits and misses on the GPU. And I would say generally yes, but not as much on the CPU. It's not your first optimization target because generally they do have caches, but they're quite small. And you should be striving for increasing parallelism on the GPUs. So if you don't have enough parallelism, then anything you'd like to do, anything you're going to do cache related, it's not going to pay off. So it's just a later level optimization.
So if you look at the first slide, that the slides that I presented initially, you will see the comparison between CPU and GPU, and you see how much cache is dedicated on the CPU die compared to the GPU. So in GPU, you have your first point of, you have to take advantage of the much larger number of compute power that is available on the GPU. So a cache is a secondary thing, while on the CPU, it's the main. And we will see also how the way that these memory transactions take place on the GPU is different from the CPU, and you have to program it with a different mindset, because something that was optimized with the CPU in mind won't work good on the GPU. So once you do this testing for the timing, please report on the Q&A. If you see anything strange or if everything goes well. Is there a reason for naming the Cuda function with an underscore at the beginning? No, it was just a convention that we used here. So in general, if you program in Cuda C++, there is a different prefix that you, not prefix, a different specifier that you put at the function to tell it that it's a kernel. So we added this underscores here just to know that this function is a kernel for our convenience. It's not needed. So has anyone done the timing? Try running on a separate cell, like I told you, without the definition of the kernel, to make sure that you don't measure also the overhead of the compilation. And try different with with different, try measuring with different vector sizes to see how it affects this time. Okay, someone wrote that the Cuda version seems to be faster only for the big arrays, bigger than 10% of the total GPU memory. Can you try with different dimensions and see if there is any difference with the execution? Like try with 10,000, for example, and then try with 1 million and measure the time it takes on the GPU. Okay. So one person wrote, the GPU time does not depend on the dimension. So let's see it. So I have here like I have a large vector here, I run. So here the GPU took 230 microseconds, and then I have N 200. I run. I run again, so more or less on the same level as before. You run again. So let's run many times. And here. So isn't it strange that the size of the vector does not make any difference? Because here we have a size of 200, and here we have 100,000 times more elements. So it seems like the dimension does not have any effect. Does any of you have any idea why this is happening? You can write the Q&A. So a person wrote, the overhead due to the transfer of arrays to device and host is larger than the computation itself. In this case, we just measured the kernel So it's just this line. We didn't measure the host to device and device to host. Another question was, what is the difference here when we add this? So with this, you tell it how many times, how many runs to do with the R4. But I will tell you what the problem with this is before we go to lunch. So one thing that I did not mention is that the host sends the Cuda, the kernels to the GPU and then returns directly. It doesn't wait explicitly for the computation to finish. So actually what we were measuring all this time here was just how much time it takes for the host to launch the kernel on the GPU. We did not measure how much time the computation actually took. So the host just sends the GPU the actual computation, the kernel, and with the grid size and the block size, and then returns, and the GPU does its computation. So you have to explicitly tell it to wait if you want to wait for it. Of course, here the computation will have finished in order for the transfer to take place, but here we measure only the kernel launch. So we don't take into account the actual computation. So you don't see any difference, an important difference when we change the size. While in Numpy, we actually measure the whole computation correctly. So you see a large difference between 200, which took 7.7 microseconds, and 20 million, which took, of course, much longer, 81 milliseconds. So we will see on the next notebook how we're going to measure correctly the time it takes for the actual computation and also the transfers. And we will also answer to that the transfer takes more time. So we will measure how much time and how much time it takes for the whole transfer to take place and how much time is actually used for computation. So I think that we can stop here and do the lunch break. But in the meanwhile, if you have any questions, please add them to the Q&A. Yes, so the question is, the typical workflow for GPUs is initiate data on the host, transfer to GPU, compute, and then transfer the result back to host. So yes, this is the typical scenario. You can also initiate data on the GPU, and we will see how we can do that. And also when we use CuPy late in the afternoon, you will see that. But typically, yes, the GPU cannot operate on its own. So the host is the director here. So it has to direct how the computation takes place and how the memory allocation. So the host tells the GPU how to allocate the memory, transfer the data to the GPU, and then it tells the GPU to transfer back the data. It asks for the data from the GPU to be transferred back. And we will see what is the cost that we pay for these transfers and why it is important to keep the data as long as possible on the GPU and transfer only back to the CPU when it's really needed. So sometimes if we use the virtual memory, this transfer to the GPU is not explicit by us, but it will take place. So after the lunch break, we will return at 1, and we will see something more complicated also with 2D grid, and we'll see how fast is the memory transfer compared to the computation, how to take advantage of shared memory, and how the memory patterns that we use for our computations are different, have to be different than the ones that we are using for the CPU because of the way that CPU handles the memory.